Welcome to this ST Microelectronics online seminar. The presentation will be focused on the PM8800A, an integrated powered device for standard and high-power Power over Ethernet applications. After a short introduction to PoE technology, a detailed description of the PM8800A together with application information will be given. Efficiency measurements will be presented for some representative cases based on evaluation boards available from ST. Power over Ethernet technology is today widely adopted to power appliances connected to a LAN cable. The IEEE 802.3AF specification, released in 2003, specifies how to safely power devices up to 12.95 watts through the Internet. There is a new ongoing standardization process which will allow devices to be powered up to 30 watts. The new specification will be IEEE 802.3AT and will be known as PoE+. The figure represents the architecture of a PoE system. On the left, there is a schematic representation of the so-called power sourcing equipment, or PSE, while on the right, a powered device, or PD, is shown. The PSE uses 2 out of the 4 twisted pairs in the Ethernet cable to supply the powered device with 48 volts DC. Alternatively, power can be delivered using data pairs or spare pairs. The powered device has to support both power options, taking into account that either voltage polarity is allowed. Diode bridges at the input of the powered device ensure that no polarity issues arise. A DC to DC conversion stage in the powered device is required to supply the circuitry from the 48 volts delivered by the PSE. PoE is based on the Ethernet standard, which is a worldwide standard, and so is widespread in the companies, small offices, and home offices, as well as some home installations. PoE lowers the installation costs because the terminal does not require an external wall adapter. It eases the deployment of such appliances since they no longer need to be close to the power source. This is specifically applicable to, for example, wireless LAN access points which had to be placed on the roof or on the ceiling. These terminals will be reached by only one cable, the Ethernet one, and not an Ethernet cable plus the power supply. The powered device can be powered up or down remotely by the PSE, for example, to save power during the night or during the weekend. Moreover, if a UPS is available, this can also ensure the service during a blackout, something that cannot be ensured with regular installations. Here are the major driving applications for PoE technology. Voice over IP phones and wireless LAN access points are early adopters. Security cameras are another well-established market for PoE. And other applications are emerging now, such as WiMAX, CPE, RFID readers, and some metering appliances that are connected to the local area network through the Ethernet cable. All of these applications take advantage of being connected directly through the LAN without local adapters. Let's now describe the electrical handshaking between the PSE and the powered device as defined by the IEEE 802.3AF specification. The PSE must first detect whether a powered device is connected. This is done by continuously polling the PSE port for the signature resistance of 25 kiloohms plus or minus 1% and associated signature capacitance. The voltage level in the detection phase is chosen so as to avoid damaging non-PoE devices. After having identified the presence of a PoE-capable device, the PSE may then progress to the classification phase. In this phase, the PSE supplies the powered device with a voltage in the range of 15.5 to 20.5 volts and senses the current flowing in the cable. The IEEE 802.3AF specification defines 5 classes of power for the powered device. Class 4 is reserved in the IEEE 802.3AF application and will be used in the forthcoming IEEE 802.3AT application for power above 12.95 watts. After successful identification, the PSE increases the output voltage to its operating value, and the powered device interface can proceed to the inrush phase as soon as the voltage at its port is above the undervoltage lockout threshold. Now let's consider the PM8800A, the integrated PoE powered device solution from STMicroelectronics. The PM8800A integrates a fully compliant IEEE 802.3AF interface together with the 25 kilo-ohm signature resistance and a current mode PWM controller. It is built using a 100-volt process. Its internal hot swap MOSFET has an RDS on of 0.5 ohm, and it is rated for up to 800 milliamps. Because of its high current capability, the PM8800A is also able to support pre-standard mode, allowing power delivery up to 30 watts. It works with power either from the PoE or auxiliary sources, which provide greater flexibility when available. With the PM8800A, it is possible to set the priority of the auxiliary sources with respect to the PoE. Programmable inrush and DC current limits are available with the PM8800A. The device also features thermal shutdown and overcurrent protection, while the integrated PWM controller features programmable switching frequency and programmable soft start. The PM8800A supports both isolated and non-isolated configurations. In the isolated one, it can be configured in flyback or forward topologies with synchronous or diode rectification. The PM8800A is housed in an HTSSOP16 package, which has an exposed pad to give better thermal behavior. Here we can see the internal block diagram of the PM8800A. Depending on the voltage on the input port, different blocks are activated to comply with IEEE 802.3AF. In the detection phase, the PM8800A enables the internal signature resistance, so it presents a 25 kilo-ohm resistance at the input port. During classification, the signature resistance is disconnected and current flows into the external resistance connected between the R-class pin and VSS node. The value of the resistance is chosen such that the current flowing corresponds to the required power class of the appliance. Once the voltage at the input port is higher than the internal undervoltage lockout threshold, the inrush phase is active and the internal hot swap MOSFET is closed in a safe and controlled way. The current in the inrush phase is programmed by the aux IRL pin, while the DC current limit is programmed through a resistor applied on the DCCL pin. Once the inrush phase has been completed, the NPGD pin is asserted and the integrated DC to DC controller is activated. Note that there is an internal high-voltage startup regulator that supplies the device at the beginning of the switching operation until VCC is available from outside, as for example from an auxiliary winding. The PM8800A integrates an advanced current mode PWM controller that operates in both isolated and non-isolated configurations. In non-isolated topology, the internal error amplifier is used, while it is disabled for isolated topologies. The device features 80% maximum duty cycle with internal slope compensations. It features several protection functions, such as cycle-by-cycle overcurrent protection, a second level of overcurrent protection for severe overcurrent conditions, and thermal protection. Spikes on the current sense are masked for a duration called leading-edge blanking, typically 70 nanoseconds. The DC to DC converter features a programmable soft start and a programmable switching frequency. A simplified application diagram for an isolated topology based on the PM8800A is shown here. For the sake of simplicity, a diode rectification configuration is shown. A detailed diagram of both the diode and self-driven synchronous rectification PoE section are given in an application note on STMicroelectronics' website. Diode bridges provide the right polarity irrespective of the input polarity. This is valid for both cases of power delivery through the central tap of the Ethernet transformer or from the spare pairs. A transient voltage suppressor, or TVS, is typically applied at the input of the powered device after the bridges, in parallel to a typical 100 nanofarad input capacitor required for the signature phase. The TVS absorbs the energy associated with the overshoot transient, ringing, etc., which may occur in the Ethernet cable. In typical designs, an SMA-J58A is used. This TVS has a standoff voltage of 58 volts, and its clamping voltage for a standard 10-1000 microsecond transient is 93 volts. The PM8800A is able to withstand transient voltages up to 100 volts without any damage. This technological feature is important when selecting a PoE-powered device. Pins on the left side of the PM8800A are related to the powered device interface, while the ones on the right are related to the DC to DC section. It is possible to program the power class, the inrush current limit, and the DC current limit by acting respectively on the R class, AUX1 IRL, and DCCL pins. The source and the drain of the internal hot swap MOSFET are respectively VSS and GND. For the DC to DC converter, the soft start duration and the switching frequency are set using the SS and RT pins. The current is sensed on the CS pin, while the loop is closed on VFB for a non-isolated topology or on comp for an optocoupler-based topology. GD is the primary side MOSFET driver. VCC is the pin that supplies the circuit. In the startup phase, the internal high-voltage startup regulator outputs an 8-volt reference. As soon as the DC to DC converter reaches regulation and the auxiliary winding of the transformer provides a voltage higher than 8 volts, the internal regulator is switched off to save power. A non-isolated topology is shown in this diagram, showing a buck topology. Only one MOSFET can be driven, since the PM8800A has a single low-side driver. Two options are available for PoE designs with an auxiliary source by using 2 pins on the PM8800A. By pulling up the AUX1 IRL multifunction pin to the external source, the PM8800A is activated even if the level of the external source is lower than the internal undervoltage lockout threshold. This is specifically suited for 24-volt based terminals, like most security cameras and medical appliances. The inrush current limit is set to its default profile, and the DC current limitation is applicable. No predictable priority of one source can be guaranteed in this case. When connecting the auxiliary source, as in this diagram, the priority of the auxiliary voltage with respect to the PoE can be guaranteed. So, by pulling up pin AUX2 to the external voltage, if the device is operating from the PoE network, the interface is disabled and the device starts regulating from the external voltage. If there is no PoE, only the DC to DC portion is active, and the device regulates from the auxiliary voltage. No PoE signature can be performed since the powered device interface is disabled. In any case, priority is a programmable feature. Since in this configuration the only active block is the DC to DC converter, no inrush or DC current protection is allowed through the hot swap MOSFET. Besides, other protective functions are available, such as cycle-by-cycle and severe overcurrent protection, as well as thermal protection. Let's summarize the key advantages of the device. The level of integration is very high, so the PM8800A integrates not only the interface, the PWM controller, but also the signature resistance. The device's technology has 100-volt maximum absolute rating, which is especially good if there are transients on the line, which can easily reach high values. As for the integrated hot swap MOSFET, it has the lowest RDS on the market, which is especially good for low power losses. The PM8800A can sustain up to 800 milliamps, enabling pre-standard mode, so power up to 30 watts is available with this device. Other features are programmable inrush and DC current limits. The inrush current profile is optimized for quasi-constant power dissipation during the inrush phase. The switching frequency is programmable. We can also connect the auxiliary source in a flexible way with two applications. One features priority of the auxiliary, losing the protection through the hot swap MOSFET. The second option offers the possibility of connecting external voltages to the PM8800A as if they were PoE lines, even with the voltage lower than the undervoltage lockout threshold. Now, let's consider the evaluation boards. Two different power scenarios can be supported by populating the same board with different components. The first board scenario targets standard PoE applications with up to about 10 watts as output, meaning 12.95 watts as input. The second supports up to 20 watts as output, which is twice the value expected with IEEE 802.3AF applications. This board configuration can show capabilities of both high-power applications and of working with wide input voltage auxiliary sources. This is allowed by the transformer selection. Two different output voltages are possible in both power cases, 5 volts and 3.3 volts. The board intended for IEEE 802.3AF applications is shown. On the top, we have two RJ45 connectors, plus the data transformer. The input connector for data and power is on the left. The second connector is where the Ethernet data is bridged. Then on the left there is the input section with the diode bridge, the input protection, and the input capacitance and filter. The PM8800 is at the bottom center of the picture. Two input jacks are available to test the two auxiliary source connections on the PM8800A. The power transformer is in the center of the picture. Note that there is also a footprint for a larger transformer, which is mounted for the 20-watt board. Just below the transformer, there is the primary side MOSFET. On the right of the PM8800A, there is the optocoupler surrounded by the compensation network. Last is the rectification diode. The same board can be populated to support synchronous rectification. This can be done by mounting the MOSFET on the back of the board. Here is the 20-watt output-capable board mounted with a larger transformer because of the higher power. The input filter, instead of using a diode bridge, uses a Schottky diode with no rectification diode at the secondary side, because synchronous rectification is implemented and the synchronous MOSFET is mounted on the back. The topology implemented here is self-driven synchronous rectification, meaning that no additional gate transformer is needed to drive the MOSFET at the secondary side. In the next two slides, we show some efficiency measurements taken from the evaluation board and provided in the application note, which is on the web. Let's examine first the device 5-volt output high-power board with synchronous rectification. The blue curve is the efficiency measurement we can expect for the DC to DC portion of the device, which is basically the efficiency measured due to the flyback section only. It does not take into account the losses on the data transformer, the input bridges, the internal hot swap MOSFET, and the consumption of the device itself. The red curve takes these losses into account and so gives the overall efficiency measurements. Note that the high-power diode bridge implemented with the power Schottky diodes and data transformer are intended for a high-power application, while the 10-watt board uses a standard diode bridge and standard data transformer. With this configuration, we can expect peak efficiency at 85% at 4 amps output. This chart shows a 10-watt 5-volt PoE power supply with diode rectification configuration, using a regular diode bridge and standard Ethernet data transformer. As in the previous chart, the blue curve is the efficiency measurement we can expect for the DC to DC portion of the device. The red curve takes into account all losses from the input of RJ45 to the output connector. Overall, the efficiency at 10 watts is in the range of 82%. In this last chart, we compare in a general way the overall efficiency measurements for a 5-volt output obtained with 3 different configurations. The black and green curves are respectively the diode and self-driven synchronization rectification cases presented in the previous diagrams, while the blue one is related to a synchronous rectification application in which a gate transformer is used to drive the MOSFET at the secondary side. Note that for high-efficiency PoE designs, the synchronous configuration employing the gate transformer provides the best result, reaching about 90% of overall efficiency, while the diode rectification is more indicated for design where cost is the key decision parameter. Self-driven synchronous rectification is instead applicable to designs targeting either up to 20 watts or when auxiliary voltages are present and their voltage is as low as 12 volts. Priority of the auxiliary source can be guaranteed and bomb saving can be obtained by managing the auxiliary connection directly in the PoE section instead of using additional DC to DC stages. In conclusion, the high level of flexibility and advanced features in the PM8800A allow various trade-offs between cost and performance available to PoE designers. Various collateral materials are available on ST Microelectronics' website, including the PM8800A flyer, together with the datasheet and application note AN2783. The order code for the evaluation board is eval PM8800A-HP. Thank you very much for your attention.